Good morning, or good afternoon, or good evening. Welcome to another video. We're going to be looking at more stuff on indices and surds, proving some more results and the laws of indices, following on from the previous lesson, chapter 1.1, and then going to apply them by looking at some worked examples, some student activities, and finally an examination style example. So first of all, as ever, there's a warm-up of 4 questions. Here they are. Try them now without playing the video and cheating to just copy down the answers. Try them yourself and then look at the solutions afterwards. So start with question 1, then obviously follow through to question 4. When you're ready, play the video again. So let's have a look together at the solutions to question 1. So for question 1, we've got these laws of indices, which we can remind ourselves from last time. Using these laws, let's write the following in index form. So first of all, 3 to the half times 3 to the half. So all we need to do here is just remind ourselves that we add the powers when we multiply. So 3 to the half plus half is the same as 3 to the power 1, which is obviously just 3. In the same way, 2 to the third times 2 to the third times 2 to the third, that's 2 to the power 3 thirds. 2 to the power 3 thirds, well, 3 thirds is obviously just 1, 2 to the power 1 is just 2. In a similar way, we can do this with a to the power a quarter. So using this law here, power of a power, we multiply the powers. So this is going to be the same as a to the power of a quarter multiplied by a quarter. So a quarter times a quarter times 4, is obviously going to be 4 quarters. That's the same as a to the power 1, and anything to the power 1 is just itself. What we're getting at here is the idea of square roots and such. Square roots, cube roots, and fourth roots. Question 2. So using the multiplication law of indices, power of a power, given that 3 squared equals 9, 6 squared is 36, and 2 cubed is 8, use the index law to evaluate the following. So 9 to the half, what we can do now, using this result here, is we can rewrite 9 as 3 squared. And so 9 to the half is the same as 3 squared to the half. But we can now use the power of a power law and multiply these two powers together. 2 times a half is just 1. So this is the same as 3 to the power 1, which is obviously just 3. So 9 to the half is 3, as is the square root of 9, which is 3. 9 to the half is 3, square root of 9 is 3. Here, 36 to the power half. We can rewrite 36 as 6 squared. So 36 to the power half is the same as 6 squared to the power half. Again, use the power of the power law. 2 times a half is 1, 6 to the power 1 is 6. So we can see again, 36 to the power half is 6, the square root of 36 is 6. So this power a half is actually always the same as the square root. Power half being square root. 8 to the third. So from above, we can rewrite 8 as 2 to the power 3. So just rewrite this in this way. So 8 to the third is the same as 2 cubed to the power 1 third. Power of a power, we multiply these powers. So 3 times a third is 3 thirds, which is obviously just 1. So this is the same as 2 to the power 1, which is just 2. So 8 to the third power is 2. And the cube root of 8, as you know, is 2. So in the same way as power half being square root, power 1 third is cube root. So we're going to prove this later on, more generally speaking. Warm-up question 3. We've got this fraction here below, and what we want to do here is to rewrite this fraction in the form 1 over 3k. So as we can see, we've got 3's just everywhere, so we can cancel some of these off. So we can cancel this 3 with that one, with 1 below. So on the top, all the 3's have cancelled, so we can just change that to a 1. And on the bottom, we have 1, 2, 3, 4, 5 of them left. So this is the same as 1 over 3 to the power 5. Part B, using this division of indices laws, we can rewrite this 3 squared over 3 to the power 7 as 3 to the power of 2 minus 7. 2 minus 7 is minus 5. And so this whole fraction here, written in index form, was this, and is the same as 3 to the power minus 5 which is the same as 1 over 3 to the 5. So for part C, what can we deduce? Well, we can deduce that 1 over 3 to the power 5 is the same as 3 to the power minus 5. And so we have a negative index. It's the same as the reciprocal of this base to that positive index. And again, this is true more generally speaking, which is what we're going to prove in this session. Question 4, we're going to expand this term here. So what we do here is we raise everything to the power 5. So this is the same as 2 to the power 5 multiplied by x to the power of 1/3 itself to the power 5. 2 to the power 5 is 32, and x to the power 1/3 to the power 5, power of a power, we multiply the 1/3 by 5, which gives us 5/3, and that's as simple as we can go. So let's crack forward with the main bit of this lesson. So, what we want to do is extend the laws of indices. So, on that note, we can use the laws of indices to define what we mean by negative and fractional indices by removing restrictions in the exponents from just natural numbers to allow integers and rational numbers to become powers too. John Wallis in 1655 was the first person to do so. The extended definition leads to a set of rules that can actually define new expressions like 2 to the power half in a natural way, which is no longer just a shorthand representation. It has more deeper meaning. So at A level, we're concerned with only rational powers, so you can breathe a sigh of relief. We can have irrational powers too, which you'll, for example, maybe see in further maths if you're studying that. So the rules don't naturally extend to irrational powers. So accepting that 2 to the power of root 3 exists, and your calculator will show the value of it, that's different to actually understanding what that means and where it comes from. But as I say, we don't need to worry about that too much right now, so don't dwell on that for too much. So we saw in the earlier example that 3 to the power half times 3 to the power half was equal to 3. So why is that? So it means that 3 to the power half is being squared, and it gives the base itself. So a base to the power half all squared gives the base. As a mathematical statement, that's the same as saying 3 to the half all squared is 3, which we can obtain from the power of a power law. Going a bit forward, we did this with 2 to the power 1/3 as well. So anything to the power 1/3 cubed will give the base itself. So now we can generalize and prove these results. So the first thing I want to prove is that a to the power 1 over m is the same as the nth root of a. So what I need to do first of all really is just define what I mean by the nth root of something. So let's define the nth root of a as follows. All this means is that the nth root of a, it's the value which, when multiplied by itself m times in a row in succession, equals a itself. So when m equals 2, that's the second root, which is just called the square root. That's very familiar, just a tick symbol with the base on the inside. When m is 3, the third root, that's called the cube root of a. Has a little 3 there. Generally speaking, when it's not just 2 or 3, the nth root of a is written as a little m above the square root symbol and then the base. So the only time we don't put a number next to the square root, next to the root, is when it's a square root. So for the square root, you can imagine there's like an invisible 2 by the root symbol here. But you don't need to include that. So now we've defined what we mean by this m tick a by the nth root, we can go on and derive this law. So let's take it step by step. So first of all, what I want to do is define y to be the nth root of a. It just makes it neater to define. And so I'm going to say that y is the nth root of a. So what that means is that if we took y and multiplied it by itself m times in a row, that would equal a. But let's think of something else. Let's just think of if we multiplied a to the 1 over m lots of times. In particular, what if we multiplied a to the 1 over m like this, m times in a row? What would that equal? Well, remember, when we've got the same base, we simply add the powers together. So if we've got m lots of this, that would be 1 over m plus 1 over m plus 1 over m, m times. So that would equal a to the power of m over m, because 1 over m times m is m over m. But m over m is obviously just the same as 1, and a to the power 1 is just a. So we can now compare this bit to that bit. And so if I put this underneath here, we can compare and pair them up. So let's have a look at this. So from this bit here, we have the first line. So just colour coding it. From this bit, we have this. And from the second part we mentioned, which is over here, we have the second line. But we've got m lots of y, and we have m lots of a to the power 1 over m, both equaling the end same thing, the end result a. And so what we can do is we can obviously just pair these up. Whoops, that wasn't what I wanted to do. So if we were to pair these up, like so, you could see that each y must be the same as a to the power 1 over m. It just seems obvious, doesn't it? Each one of these must be the same as each one of these. So we can formalize this now by saying that each y must be the same as a to the power 1 over m. But what did we define y as in the first place? Well, we defined y as y equals m root a. We defined y as the nth root of a. So therefore, the nth root of a must be the same as a to the power 1 over m. And so we have our result. We wanted to prove this, and we have here. Granted, I wrote them in the opposite order, but you can see they are exactly the same thing. The second derivation, a to the power n over m, I want to prove that it's the nth root of a to the n. This is very similar to the first proof. So I'm going to set out by defining z as the nth root of a to the power n. In other words, z is the nth root of a to the n. So using that, what this means is that if we take z and multiply it by itself m times in a row, we're going to get a to the power n, by the definition of the nth root of something. However, what if we took a to the power n over m and multiplied that by itself m times? Well, what we'd have is this, a to the power n over m multiplied by itself m lots of it. But using the first law of indices, where we just add the powers together, n over m plus n over m, do that m lots, we'd have a new power of a of mn over m. Now, the m's will obviously cancel. So we could cancel the m on the top and the m on the bottom, which will leave us to just a to the power of n, which is exactly the same as z multiplied by itself m times. So now we can put this below this and compare. So very similar to before. So from this line at the left, from this line, we have this statement here, and from the bit on this right hand side, we have this bit on the bottom. So we can pair these up. We've got m lots of each multiplied together, and it equals the same thing. So it stands to reason that each z must be the same as each a to the power n over m. So if we write this down formally, each z is the same as a to the n over m, but we define z as the nth root of a to the n. So therefore z, which is the nth root of a to the n, must be equal to a to the power of n over m. So again, we've proven what we set out to prove. Just colour code it for no reason whatsoever, because I like colouring things in, because maybe I've never grew up. I don't know. Anyway, there you go, some nice blue for you. And it's proven. Derivation 2. The third derivation. So this is a nice little trick, actually. So a to the power minus m is the same as a reciprocal of that thing to the positive power. This is a little bit of a trick, which I think is quite neat. So I'm just going to rewrite a to the power minus m slightly. I'm going to rewrite this as a to the power 0 minus m. Remember, subtract by m, that's the same as subtracting it away from 0. So why bother doing that? Well, now what we can do is manipulate this using the previous laws of indices from the previous lesson. So, a to the minus m is equal to a to the power 0 minus m, but using the division law of indices, a to the power 0 minus m is one and the same thing as a to the power 0 divided by a to the power m. Remember, when you divide indices of the same base, you subtract the powers. So 0 minus m, that's what we had here. So just a reminder that this is from last lesson, so that's where it's come from. Look back at your notes from last time if you're wondering why that is the case. We can now rewrite this in a fractional form. A to the 0 divided by a to the m is the same as a to the 0 on top, a to the m on the bottom. But remember, anything to the power 0 is obviously just 1. And so a to the power minus m must be the same as 1 over a to the m. And again, we've proven what we set out to prove. There is also a special case, and in fairness, I did mention this last lesson because I couldn't resist, it's so important. However, let's formally define it again, because it can't hurt to do it a second time. So, we need to prove a special case where m is equal to n using this division law of indices. So first of all, let's just begin by saying a to the m divided by a to the n. That's the same as a to the m minus n. However, if m is equal to n, what I can do is I can say that n is m and just substitute in m in place of this n. So then we have a to the power of m minus m, which is obviously just a to the 0. So that's the first thing to say. The second thing to say, if I just start with exactly the same thing, a to the m divided by a to the n, then I can rewrite this in terms of a fraction. So I can say that's a to the m on top and a to the n on the bottom. However, using the fact that m is n, I can replace the n with m. So that's the same as a to the m divided by a to the m. So we don't know what a to the m is, but all we do know is we've got something on the top and exactly the same on the bottom. And it stands to reason, going back to primary school, any number, anything divided by its exact self will always equal 1. So we started off with the same thing here and got two different conclusions. One yielded a to the power 0, the other yielded 1. So therefore, these must be one and the same thing. In other words, any rational number, any real number to the power 0 will equal 1. We've based a as a natural number. This is true for any rational number indeed. So let's do some examples together. Some worked examples. So using what we know now, we can crack forward and work these out using the laws of indices. So simplify, writing each as a positive value of x, 3x to the half times 4x to the 3 over 2. Do the coefficients first. So 3 times 4, that gives us 12. The powers of x, remember we just add the powers together. So a half plus 3 halves, that gives us x to the power of 4 halves. But I'm hoping you know that 4 halves is the same as 2. So that just becomes 12x squared. Part B, same idea, but just dividing. So do the coefficients first. So 15 divided by 3, that gives us 5. When we divide when we have the same base, we subtract the powers. So the new power of x is going to be a half minus a half. Minus a minus gives us a plus. So half plus a half is x to the power 1. Because it's power 1, we don't need to write the power, just leave it as x. So this is the same as 5x. Part C, same idea but now in decimal form, but the same rules apply. So coefficients, 2 divided by 4, let's leave this in the same decimal form because we've got decimals here, so let's be consistent. So that's going to be 0.5. Now we need to think about what the new power of x is. Well, we're dividing powers of x. When we divide, we subtract the powers. So 1.5 minus 0.25 is going to be the power 1.75. Part D, cube root. So we're going to cube root everything inside here. So it's the same as the cube root of 8 multiplied by the cube root of x to the power 6. Cube root of 8 is 2. And we can think of the cube root of x to the 6 as x to the 6 to the power of 1/3. So 6 times 1/3, that would give us x squared. As a double check, just think about multiplying x squared by itself 3 times, you would get x to the power 6. Part E is more of a throwback to last lesson to make sure those skills are consolidated. So we're going to just take each term individually and divide it by x to the 5. So the first one is going to become 7x to the minus 3, because 2 take 5 gives minus 3. And then minus 2, x to the power 1 divided by x to the power 5 is going to be x to the power minus 4. Some more worked examples. So we've got here to evaluate these as simply as possible. Part A. Just remember, power half is exactly the same thing as square rooting. So 9 to the power half, that's the same as the square root of 9, which is 3. Part B, 1/3 means cube root. And so this is the same as saying it's the cube root of 27. So what number times itself 3 times in a row gives us 27? Well, that weirdly is again 3. Part C, if you've got something like this, what I would suggest doing is to use the power of a power rule. And think about this as a unit fraction to the power of the numerator. So you could rewrite this, I'd suggest, as 64 to the 1/3 squared. Because by the power of a power rule, 1/3 times 2 is 2/3. So now we'll always try and take the root before doing the squaring or cubing. Some examples are different, but generally speaking, root it first, then do the square or power after. So 64 to the power 1/3, that's the same as the cube root of 64. So the cube root of 64, then squared. The cube root of 64 is 4, so we have 4 squared, and 4 squared, whoops, my PC went a bit slow there, sorry. So we have 4 squared, which gives us 16. Part D, again, we can use this power of a power rule. So start with 49 to the minus 3 over 2. And I'd suggest we write this as 49 to the power 1/2, then to the power minus 3. Then just remind yourself that the power of a half means square root. So 49 to the power 1/2 means the square root of 49, which is 7. So we have 7 to the power minus 3. Anything to the minus power is the same as 1 over that same thing to that positive power. So 7 to the minus 3 is the same as 1 over 7 cubed, and 7 cubed, 7 multiplied by 7 is 343. And so the final evaluation of this one is it's 1 over 343. Next up, we have an activity for you to try. And so we've got 12 different tiles here. The idea is to work out the value of each one, and then afterwards label them from 1 to 12 in ascending order. So that means smallest first, going bigger as you go along. So pause the video and have a go at these, number them yourself, and then only once you've done that, play the video. So let's have a look now and see what we get. So you can do them in any order, obviously. What I'm going to do, I'm going to put the value of them in the bottom corner. So we can do them in any order. I'm going to suggest we do the easiest first because, well, it's just more tempting. So this one here stands out. 4 to the power 0. Well, anything to the power 0 is just going to give us 1. Fairly easy as well is 16 to the power of a half. 16 to the power of a half is the same as 4. So this tile here is the same value as 4. A half to the power of minus 1, just picking this up because it's just there, that's going to be the same as 1 over a half to the power of 1. Remember, negative powers is the same as 1 over the positive power. So 1 over a half is the same as 1 divided by a half, which is actually 2. So this one here is equal to 2. 125 to the power 1/3, that's the same as a cube root of 125. The cube root of 125 is 5. So I'm going to write 5 here. 27 to the 2/3. So 27 to the power 2/3, that's the same as saying it's 27 to the 1/3 squared. So it's the cube root of 27 squared. The cube root of 27 is 3. So 3 squared is going to be 9. So this tile here is going to be equal to 9. This one, 8 to the power minus 2. 8 to the power minus 2 is the same as 1 over 8 squared. So this one's going to be 1 over 64. Which one to do next? As I said, it doesn't really matter. Let's try this one. So 4/9 to the power minus 1. That's the same as 1 over 4 over 9 to the power 1. That's just the same as 1 over 4 over 9. So 1 over a fraction, we can turn this fraction on its head and just rewrite it as 9 over 4. Which, if you want a decimal, is 2.25. So that one's 9 over 4. Not too many more to do now. This one here isn't too bad. 25 to the minus half, that's going to be the same as 1 over 25 to the positive half. So 1 over 25 to the half, power half is square root, so 1 over the square root of 25, that's 1 over 5. Let's have a look at this one here at the top. 1 over 5 to the power minus 2. Well, that's going to be the same thing as 1 over, let's just write it out like this, minus 2. That's the same as saying it's 1 over 1/5 squared. Now, 1/5 squared is the same as 1 squared, which is 1, and 5 squared, which is 25. So that's 1 over 1/25, which is going to be 25. So this one here is 25. So almost on all of the tops. Here, like I said, 9 to the power 3 over 2. Do the root first, the power after. So power half is square root. So square root of 9 is 3, and then we can do 3 cubed, which is 27. So that one's 27. I've left the hardest ones till last. So this one here, 1/16 to the power minus 3 over 2. And so this one, what we could do is think of this as the power half and then to the power minus 3. So it's the same as saying it's 1/16 to the power half, and then we can do that to the power minus 3 using the power of the power law. So what's the square root of 1/16? We can square root the top and square the bottom. This is going to become a quarter. So we're going to have 1/4 to the power minus 3. That's going to be the same as 1 over a quarter cubed. There are different ways of doing these. I might be actually going the long way round here. just to show you that it is all consistent. So a quarter cubed, I shouldn't really be writing line after line, but just to save space, a bit naughty, but never mind. So a quarter cubed, 1 cubed is 1, 4 cubed is 64. So 1 over 1/64 is actually the same as 64 itself. So this one's equal to 64. Finally, this last one in the bottom right corner. So I'm just going to make some space and show you this one slowly. First thing I hope you notice here is we have a mixed number. What you'll need to do for this one is to change this into a top-heavy fraction. So 1 and 7/9, that's the same as 16 over 9. 16 over 9, and that's to the power of -1/2. Okay, what I suggest we might want to do is think of this as the power 1/2 and then to the power -1 after. And so we can think of this as the square root of 16 over 9. The square root, remember, is power half. And then all of that to the power -1. Just remember, power of a power law. Power 1/2 to the power -1, that will give us a -1/2, which is what it is. So square root of 16 over 9, we can just square root at the top and then square root at the bottom. So this just becomes 4/3. So 4/3 to the power -1 is just 1 over 4/3. So we can just turn this fraction on its head and we arrive at 3/4. So therefore, this one in the corner is 3/4. So it might take a while to do all these powers and simplifying them, working out the values, but it's what we need to do, and it's good practice. So now we've got all these values, we can actually begin to order them, smallest first. The smallest is this one, 1/64. So I'm going to put the order in red. The second one, bigger than that, is going to be 1/5, which is this tile here. Bigger than that, slightly, is 3/4. Bigger than 3/4 is this one, which is equal to 1. The fifth tile is this one over here, which is equal to 2. Bigger than 2, we have 2.25, which is this one, 9 over 4. A bit bigger than 9 over 4. Number 7, we have 16 to the half. After number 7, we have this one, which is equal to 5. The ninth one is 27 to the 2/3. The 10th one we have would be this one over here, which is 25. Slightly bigger than 25 is 27, so this tile is number 11. And the last one, the biggest one, is 1 over 16 to the power -3 over 2, which is 64. So that's the numbering you should have got yourselves. Finally, let's have a look at an examination style question here. So for this one, we've got that y has been defined as 1 over 16 x squared. So using that definition of y, we need to work out what y to the 1/2 is. So y to the power 1/2. So y to the power 1/2, using this definition of y, is just going to be the square root of all this. So y to the 1/2 is 1 over 16 x squared, all square rooted. So we can square root the number first and then square root x squared. The square root of 1/16 is a quarter. The square root of x squared is just x itself. So although it might look intimidating because of how it's worded, it's actually not too hard, part A. Part B is a bit harder, but again, not so bad. So for part B, we want to have 4 lots of y to the power -1. So what I'd suggest, first of all, is thinking what y to the power -1 is. Forget the 4 for a moment. To the power -1 means 1 over y. So that's 1 over y which is 1 over 1/16 x squared. 1 over 1/16 is 16. 1 over x squared is the same as saying it's x to the minus 2. So if that's y to the minus 1, we can say that 4 lots of y to the minus 1 is this here multiplied by 4. 16 times 4 is 64, so we're going to have 64 x to the power minus 2. And that's all there is to it. Apart from, of course, you need to do the hard work yourself as well. So using these notes and following on with what I've said, apply it yourself. I want you to try these questions on page 11, exercise 11D in the book. These parts of question 1, then 2, 3, 4 and 5. Try every part I've suggested, check your answers using the back of your book. If you're not arriving at the same solutions, double check or ask a classmate. If that's not working, check your notes. If you're still not sure, ask me by asking in class, dropping me an email or leaving a comment in the comment section or seeing me in Achieve. So good luck with those, be in touch if you're stuck and you'll hear from me soon. Thanks for now.